My name is Keith Hudgens. I work for Docker. I'm working technical alliances for Docker. My main specialty and focus is working with basically you guys, storage providers and primarily engineers and developers from the storage community who are wanting to plug their tools into Docker storage APIs. I write the tests to maintain all of the storage integrations and things like that. So, that's why theater major with a UGA ball cap is talking to you guys. Getting started. So this talk is primarily an overview of the container landscape, who's involved, which companies and which open source projects are involved in things, and then what the various APIs are and kind of what they look like. So let's get started first with kind of the big umbrella organizations that are responsible for governing the container standards. Primarily it's the Cloud Native Computing Foundation. Subset of that is the Open Container Initiative. So CNCF is basically the governing body that basically determines the standards of what the container formats and container runtimes look like. Open Container Initiative is specifically the container runtimes. Both of these are part of Linux Foundation, which has been around for a good long time. So the container runtimes themselves, I'm going to run through this really quick. First of all, there's Docker. Docker's been around since the beginning of the container explosion, and we'll talk about the timeline of that in a little bit. It is the default container install for almost everything except Red Hat. We'll talk about that in just a second. Docker Community Engine, which is basically the free to use version of Docker Engine, has over 20 million installs. It's by far and overwhelmingly the biggest install base. But there's also Containerd, which is a CNCF project that was originally carved out of what used to be open source Docker around 2016. It's a fully graduated CNCF project, so it's got a full code base that's maintained and supported industry-wide by engineers. It has a Windows and a Linux container runtime. Other than Docker Engine, it's the only container runtime that works on Windows at the moment. And then it's also upstream of Docker, at least on the Linux side. CoreOS, CoreOS, the company, was bought by Red Hat in 2018, and their container runtime was called Rocket, or spelled RKT. That was just as of last month archived by CNCF. So essentially, that is now a dead project. So if I do this talk next year, we'll probably not be talking about Rocket anymore. CRI-O is a newer runtime that was founded by Red Hat and IBM. They started it, I want to say 2016, 2017. As of now, CRI-O has a full generally available release. I forget what the current version is, but it is a fully valid and functional runtime engine for containers. It was originally intended to be the official Kubernetes native runtime by the folks that founded it. It is a CNCF project. It is fully open source. It isn't necessarily the default runtime container for Kubernetes. Kubernetes itself as a project is generally agnostic of the runtime underneath it. But CRI-O is the default runtime for Red Hat's OpenShift product. So that's the overall layout of the container runtimes as we have them right now. So let's focus on, now we're going to narrow down and focus on storage. This diagram is basically kind of the life cycle of container storage. It's a conceptual diagram. It's not actually like a fully functional map of a production layout. But fundamentally what happens is a developer creates a container. You basically take your container take your Docker file, run a Docker build or whatever other container build tool that you're using. And then you have this image that's sitting on your disk. It's just a flat image file. So typically what happens is that gets uploaded to a registry to a container registry, which is either running as a hopefully distributed in a production environment container system in a running container fabric, or chances are it's going to be up on the cloud somewhere. The options for on the cloud, Docker Hub, I support the colors. I work for Docker, so I have to kind of pimp that a little bit. But there's also Quay.io and a few other run container storage systems as well online. I know Red Hat has one as well. And then those generally can feed into local container registries as well. So and we'll talk about how that gets stored in just a little bit. And then from there, from the registry, when you want to run a container at runtime, then it'll get moved. The container will basically just the bits will be copied locally onto the container host. So these green boxes are essentially a container host, and the container image gets dropped on disk just as a raw image file onto the disk of these boxes, and then it gets spun up. And we'll talk about how that works in just a minute. And then if your storage, if your container in your application requires persistent storage, then you'll typically have some kind of backing storage system that generally works through a volume storage that connects through a volume driver. And the volume drivers are basically, they plug in volumes, whether they're file-based or block-based, into the container at runtime. They'll get bind mounted into the container, into the container's file system when it gets started up. So this is basically just a recap of what we just talked about. There's three primary contexts for storage. There's the raw container image, which is at rest, like I said, it's a file on disk, or it's an object storage, which is backing a container registry somewhere. At runtime, you have one of several graph drivers. Graph drivers are contextual depending on the host OS and what kernel features that host OS supports, and this includes Windows. And then finally, we have persistent storage, and this is where most of the focus of the talk is going to be. But we're going to go through the first two really, really quickly. So the graph driver, actually, we're the container at rest. Real quick, I don't have a slide on it. It's literally just a disk image. At runtime, these things are managed in copy on write or Union FS style. So what happens is the container image is essentially considered immutable. When the container launches, we have this copy on write, and any diffs that get written inside the container's local file system get written into as diff layers into the graph driver storage system. And then when the container stops, we basically get rid of all the diff layers. They just get thrown out. So this is why most people talk about containers being stateless. The actual container image itself fundamentally is stateless. There's ways to make it stateful, and that's the persistent storage plugins that we'll talk about in a bit. So fundamentally, for Docker and Containerd, I've got a link here, and the slides are available, so you can download them. But to the Docker's documentation for the matrix of which graph driver you want to use. Again, the container images, containers are intended to be immutable, so you really don't want to build a container. And if you've got developers that are wanting to do container systems, tell them, do not try to put a whole lot of writes directly into the container file system. Don't do it, because what happens is we start creating a whole bunch of diff layers on that Union FS, and then if you have a whole bunch of containers doing a whole bunch of this on one host, that stack just tends to fall over. You can do a pretty reasonable amount of writing, but if you've got a really disk-heavy application that you really need that disk, you really need a bunch of writes to disk, use a persistent volume for where the writes go. Where do you draw that line? Honestly, it's a sliding scale depending on your hardware. If you've got really, really fast storage and a good processor on your container host, then you can sustain a whole lot more writes than you can if your container host is a VM on a 10-year-old box that's been in the back of your data center for a while. It just depends. Fundamentally though, don't put a whole lot of writes into your container's local file system. The idea is that when the container starts, and we'll talk about the life cycle a little bit later, but fundamentally when you start up a container, generally you're going to be running these things in an orchestration system, whether it's Docker Swarm or Kubernetes or Mesosphere, although Mesosphere is moving towards Kubernetes as well. Docker is moving towards Kubernetes as well, so we're going to talk about Kubernetes a lot. But basically what's going to happen is your application is a bunch of containers at once that are all talking together through the network. And so fundamentally, you really just don't want to maintain a lot of writes into this one local container image, particularly the fact that if you need those writes for later, then you need to put them in a persistent volume, because if whatever happens, that container gets shot in the head and falls over, you'll lose all that data. So
if you do a little bit of writes,
uh-huh.
Does the image grow?
No. Well, the core image stays constant, and we write diffs. So it's either, depending on the driver, it's either copy on write or UnionFS. But either way, under the hood, it's a little bit different. But either way, we're just writing diffs to separate files on the disk. And what happens is when the container stops for whatever reason, all of those diffs are thrown out. They're not immediately thrown out, but like you can't access them anymore. They'll eventually be cleaned up. So, and then just a list of a couple of the standard drivers. And what's interesting is like CRI-O actually uses the same drivers for the most part as Docker Engine and Containerd. LCFS is interesting. LCFS is interesting. It's actually an open source experimental graph driver that was done by Portworx a couple of years ago. It's really fast, but not a lot of people decided to use it. So, and it also runs in Fuse, unlike everything else, which is all kernel based. But not a lot of people picked up and used it, so that it's kind of languished a bit. But it's really interesting. So, just some deep links for future reference when you download the deck. Basically, fundamentally, it's documentation for graph drivers, and then some blog posts explaining the details better than I can. So now we're going to talk about persistent storage. In the container space, in the container ecosystem, persistent storage is continuously a really hard problem. We're going to talk about why that is, but this is why you do not see any container platform offering, whether it's Docker, whether it's Rancher, CoreOS, OpenShift. Nobody offers default persistent storage. Or if there is default persistent storage, it's just writing the local disk on the host, which is bad anyway. And there's a reason why. It's hard. None of us are fundamentally storage experts. We're container experts. So we rely on the ecosystem, which is why we have all these APIs. So, couple of things. This is a little bit of the history and timeline of how this stuff is developed. Containers and operating systems are totally not new. chroot was created in '79, and through there's a whole process. It was like basically really quiet for a long time until right around 2000, when a bunch more Linux-oriented container technologies started coming out. Well, Linux and Solaris started coming out, and then it kind of boiled out into Docker. And since 2013, the container ecosystem has exploded, mainly because Docker came out with some really easy tools for developers to build these immutable containers. And immutable containers are actually like that was the inflection point why this thing exploded, because now a developer can say, this is my application in one neat little package that you can throw up into Docker Hub or some other online tool. Other people can pull them down and share them, and it's very reusable. Whereas before that, they were basically, containers were just chroot jails. So that's the biggest thing. So this immutable containers thing is really important, and that's kind of the fundamental thing as to why persistent storage for containers is really a big deal. So each container is an instance of an image, just like kind of a VM in the cloud, except that unlike a VM in the cloud, the way most people run VMs in Amazon or Azure or Google or whatever is you'll spin up a VM with an OS, and then you'll take a tool like Chef or Puppet or some kind of anything like any of the config management tools, and then you'll push your changes onto that virtual machine as it comes up. So your raw image tends to be just a empty OS. That's the way most people do it. There are some folks like I mean, everybody knows the Netflix story. They build their images, they build their VM images as part of their build system, and then they spin up and spin down VMs as needed. That's the pattern that containers tend to run on. And so the idea is that your containers are going to spin up and down constantly. Your applications, the goal for containers and the design for the container fabric and these container frameworks is that applications are built of these immutable units. So each container is intended to be a fairly small piece of your entire application, and it's gone so far as to folks are talking about the microservices and that type of thing. You don't have to build your applications that way, but that's kind of the intent and the original design behind Docker is following this microservices trend, which isn't new either. That goes back to SOA, back in like early 2000s, right? So, so the idea is these containers are going to be spinning up, spinning down a lot. So say you've got like a typical LAMP stack application. So you've got a bunch of web servers, you got some load balancer on top and some kind of persistent store underneath, like your typical 3-tier application. In a container fabric, the idea is that you'd have some kind of watchdog that's keeping an eye on your containers, and you can spin up or spin down that application layer for as many containers as you need to keep up with load and keep up with demand. When you're doing a full microservices application where you have a bunch of stuff reading off of a queue, and you have it can be even more complex. And the idea is that you don't know where these containers are going to run. You have dozens or hundreds or even thousands of nodes in your container orchestration system, and so you don't even know where these things are going to start up or be. So because of that, these things spin up and spin down very, very quickly. A container, once the base container image is on a host, each container comes up in literally seconds, even on slow equipment. So big thing is not every container is going to need persistence. Application servers, things that are managing a message queue, you don't really need persistence on this. It's just parts of your application. But your data's got to go somewhere. Big thing is on this is depending on how you're managing your data and what you're doing with your data is where that stuff has to go. If it's a database, if it's some kind of object store system, whatever it is, right? So that persistence has to be managed somewhere. What most folks are doing these days is they're maintaining that data layer outside of their container fabric. You don't have to do that. For certain databases and for certain scales, it kind of makes sense. If you're dealing with a transactional database for a multinational airline with tens of thousands of transactions a second, you might not want that in containers. But for most applications, for the overwhelming majority of applications, it's of a scale that modern hardware can containerize that and run it. So a little bit of a quick timeline. This is super detailed, but the main thing that we're looking at is these 4 inflection points. The first one is the red oval there. That's when containers essentially escape mainframes. That's around 2000 when FreeBSD jails become a thing, and then not too long from that, Linux starts adding chroot and things like that as well. And that's the Linux containers is the yellow inflection point. That's when things, if you start noticing a lot of these things on the timeline, you get a lot more of them as we go this way, and that's mainly because of Linux. Linux exploded, with that containers exploded, and then the blue inflection point was Docker. That's when containers became really, really easy to use and a viable thing for packaging and managing your applications. And then very shortly after that, due to a lot of the same things that happened behind Docker, the Kubernetes project was open sourced and released from Google. There's a lot of projects from Google that contributed to the early stages of Docker's development. Google and Kubernetes and Docker, their development was, if you look at the timeline, it's actually really, really closely related, even though there was still a couple of years from Docker's release and Kubernetes release until Docker as a company started supporting Kubernetes. They are very closely related projects in the ecosystem. So about that data, right? Prior to this whole pluggable dynamic volume management that we're all about to talk about, data was stored in a bind mounted volume. So what I mean by bind mounted volume is when the container starts up, you get this, the container is essentially a CH root jail with a bunch of extra kernel protection on top of it. It's got C groups and things like that that basically wall off the process, so it's not supposed to be able to reach out to the wider system. I mean, of course, there's ways to crack that, but you know, the security is an ongoing struggle there that we've mostly kicked the tires on. But data store, if you have to have persistent data, what happens is the earliest hack was we would take a volume on the root disk of the container host and just bind mount that into the CH root jail. So basically, you've just got you've got this external folder that you can write a bunch of stuff into. The volume itself, literally just a directory on your disk. So people that were running early production systems with containers, what they would do is they would take a SAN or a NAS storage solution and just plug that into varlib Docker, which is where that directory lives in Linux. And then all of the volumes that get bind mounted are just directories on this network attached or direct attached, or you know, this big network device. Modern container storage is a little bit different. We have two primary interfaces. We got the Docker volume driver that we're going to cover really, really briefly because it's really, really simple and really, really dumb on purpose by design. And then we're going to talk about CSI, which is where everything is going. CSI is the container storage interface. It is a community standard. The Docker volume driver is basically something that Docker came up with to manage pluggable volumes. Was released in 2016. CSI GA'd at the very, very end of 2018, and we're going to go over the details of that. Along with that, prior to CSI, Kubernetes also had some pluggable storage stuff as well. They're basically what we call in-tree plugins, where the plugin was actually in the Kubernetes source tree contributed by third-party developers. There are external provisioners using the same system as well. Flex Volume, which was an earlier pluggable plugin attempt. Those are basically deprecated. For various and sundry legacy reasons, they're going to have to be maintained for a little bit longer. Flex Volume in particular is going to be the first Windows-based Kubernetes pluggable system. So they'll be maintained for a little while. But the intention is by the Kubernetes 6 storage community is to deprecate them as soon as we can. So, Docker volume drivers. It's a really simple standard persistence interface for Docker Swarm. Mesosphere also supports the API. It runs as a, the V2 Docker volume driver interface runs as a container, and some of the V1 drivers from early on were also ran as privileged containers. But essentially what this service is the volume driver itself is a REST API. It provides a REST API for Docker and Mesosphere, and then on the back end of that, it implements whatever API connection needs to be done to the backend storage system. And then for the V2 specification, which is everything but Windows, at least in Docker, we have a manifest.json file, which is and there's links in the slide or two down for that format. And what that does is that actually just specifies various kernel capabilities that the plugin container is requesting, so that you can write an API driver that needs more expanded privileges without having to run a fully privileged container on a production system, because that's generally bad news. We support all platforms that Docker runs on: Linux, Windows, the Intel processors, and ARM. You will need, if you're going to build the Docker volume driver and you want to support Windows, then you'll have to build it separately for Windows, because Windows containers running Windows runtimes need to be run under Windows kernel. Same on Linux. You can't cross runtimes, at least not yet. And then for Windows support, we use the older V1 driver API. Exactly the same thing, except that you can't. Your REST API service has to bind in the V2 driver API. You have to bind to a link local socket for security reasons. That way, you don't have a port dangling out on your management network. We support port binding on the older API, and Windows at the time that we did this didn't support link local sockets. They kind of do now, and certain releases of late Windows Server 2016, and it's intended for Windows Server 2019 as well. The interface is very, very stable. We haven't changed the API since 2017. The big thing about it is that there's no cross-node knowledge. So if you, so basically each driver, when Docker goes to schedule a container, if there's a volume that's supposed to be mounted into that container, Docker will ask the specific host, hey, do you have a container with, do you have a volume named whatever? And if it exists, it'll mount that container in. So basically, because of that, you have to expose every volume managed by your Docker volume plugin. You have to expose every volume that's been requested and created by Docker volume plugins on your entire cluster to every node. Like you can't filter it or anything. It's just because this protocol is really dumb, and it's meant to be. It's meant to be really, really highly scalable and easy to deal with. And the easiest way to make things super scalable is to make them super stupid. It's just kind of the way that works. So Docker Enterprise Edition does track volumes between nodes out of band based on the volume ID generated by the UUID generated by Docker across the installation. So we're a little bit better than we used to be, but it's still, if you're going to be writing a Docker volume driver, make sure that every volume is exposed to every host. And then we got some links basically to the documentation on how to build those things. And if you have any questions, you can always email or bug me. CSI. This is the emerging standard. This is what everything is going to. It's becoming the default. It is basically already the default for Kubernetes, not on Windows. The 1.0 spec was released in late 2018. It's going to be, I forget whether it was October or December, so I didn't specify in here. But it basically, it was the 1.0 spec came out basically like a week before the Kubernetes 1.13 release. And then Mesos and Cloud Foundry also support the CSI specification as well. Each one of those implements this slightly differently than Kubernetes does. So if you want to support your CSI drivers on other platforms, make sure you do a lot of testing. Well, so Mesosphere is a separate project, but what happened is the company that sponsors Mesosphere, which they've changed their name to like DC2I, I think. Basically Mesosphere has a separate Kubernetes install. It's basically the same thing that Docker did, is we basically just included Docker or Kubernetes in Docker Enterprise, and so you can run Swarm workloads and Kubernetes workloads under Docker. Mesosphere is doing the same thing, and you can have Mesosphere workloads or Kubernetes workloads or both. And what's happening is, and they're doing that because they have customers on the old stuff, but almost all the new customers want the new stuff. Kubernetes is extremely complicated and it takes a lot of specialty knowledge. So from the Docker side of things, we are finding that some of our customers, about, I don't know, about 10% maybe, it's a complete and total ballpark swag, but want to run Kubernetes and then decide, you know what, we're going to use Swarm anyway because it's simpler. But it's a small percentage. Almost everybody uses Kube, and it's going to be where things are going. Initially, CSI supports CRUD operations on volumes. Basically, you create the volume, mount the volume, change some metadata, delete the volume. Basically, what you can do through CSI. There's some expanded feature support that's coming, and in a very, very Kubernetes way. Underneath Kubernetes, all of these things are managed through these little sidecar containers. And if you want to run the expanded feature support, then essentially you build a separate container as a microservice for that little API feature. It's just the Kubernetes way of doing things. So the CSI drivers need three fundamental services. These are like API interfaces that are defined in the CSI spec. There's node service, controller service, and identity service. They all communicate via gRPC, which is it's a CNCF RPC API protocol. not API, RPC protocol. But anyway, so the node service primarily is dealing with node issues. So it's taking an existing volume and mounting it on the node and telling Kubernetes where it's mounted on the node so we can do the bind mount when the container launches. And also unmounting the node and releasing it back to the volume pool. And then the controller service does basically everything else. It basically creates the volumes, does all the actual like volume operations on the storage end before they get to the actual node. And then there's the identity service, which is basically kind of and well, I've actually got some slides on these. So this is a controller service. We kind of already talked about it. It's for volume operations, create, delete, list volumes, and publish operations. That's kind of a Kubernetes thing. So when a publish is basically when you take a volume from a pool and apply it to a container. That's a publish event. And a volume can't be attached to a container unless it's published. With some exceptions, which we'll talk about in a little bit for like iSCSI and NFS. Basically, if there's certain volume operations that have volumes already predefined or already mounted on the nodes, or like with NFS, it's not a volume, it's a file service. So all you got to do is when you're bind mounting a volume, you're just creating a directory. So in that case, you don't have to create or delete volumes in that case. So that's fundamentally the controller service, the node service. Again, mount, unmount, staging operations. Staging is basically if you've got a brand new block device, it's a brand new volume that you're mounting onto a box. Then you have to do prep stuff like creating a file system, setting permissions, that kind of stuff. So that's what happens in the staging. It's also used in like multiple mount scenarios if you're doing write many mounts to where you've got multiple containers that are mounting the same volume at the same time. If your backing store supports it, then you have to do some other stuff in staging just to let Kubernetes know, hey, this is a multiple write volume. And then identity service is API grease. It's basically when Kubernetes says, hey, new plugin, what things can you do? This is these are just a list of functions and stuff for publishing these things for broadcasting the capabilities of your plugin in the Kubernetes so it knows which API calls to make. So do you need two different containers for this node and controller operations in CSI? Probably. You actually can throw them in the same container if you want to. But the interesting thing there is probably only one container is doing your controller operations. And so that'll be the one that you tell Kubernetes has controller operations, and you'll define that in your application spec when you do like kubectl apply in your YAML file. And what you'll do is you'll run two separate classes in your two separate classes inside your kube app definition, one for node operations and then one for control operations. And they may be the same container, but kube's going to talk to each one of them differently. That's okay too. But we got these new things that are coming out. These new capabilities that are newer specs coming out for CSI. So these are some proposed features. None of these are fully baked yet. Volume snapshots, which I believe are going to be. I believe that's going to come in beta in Kube 1.16, if I remember correctly. And then volume resize operations. I think I got that backwards. I think volume resize is the one coming out. And then raw block volume and Windows CSI support. These are new things that are coming down the pipe. Windows CSI support's going to be probably about a year, give or take. Windows isn't even fully supported on Kubernetes. I think alpha support is intended for Kube 1.16. And we'll know if that actually releases when 1.16 drops, which is probably in a month or two. And then generally the back half of the year Kube release tends to happen around December. It may happen earlier. And then I got some links to basically the features. This link down here is on the bottom. It's where all of these are kind of very fully defined. The interesting thing about these are especially volume snapshots and the dynamic volume resize operations. These are built as a sidecar container. So you have your node controller container, one of those running on each node, because you have to actually mount the volume into each node. So you have to have one on every node that you're supporting. And we'll talk about that in a second. And then the controller container. Volume snapshot containers and volume resize op containers are also separate containers in your plugin, if you're going to specify those. So here's how you deploy those things. Now this is kind of a possible topology. This possible topology line was suggested by one of the engineers at Docker because theoretically, at least in a lot of Docker deployments, the Kubernetes master nodes are flagged for like do not launch containers on these nodes. You totally can launch containers on those nodes, but for operational reasons, it's kind of good to keep them clean. But it also kind of makes sense to put these controller plugins on there because they're separate from everything else, and they're kind of a fundamental. That's where you create your volumes. So it makes sense to put them there, but you don't have to. The drivers deployed via the kube application YAML definition, typically, but you can also write a Helm chart. You can also write a Docker Compose file if you're running Docker Enterprise, or basically any other format that whatever your Kubernetes distribution supports for launching containers, for launching applications into. You want to deploy this as a stateful set, but I personally really recommend just writing a standard application YAML for your customers. Everybody supports that. Some Kubernetes distros don't support Helm charts right off the bat. Every Kubernetes distro can support Helm charts, but it's not always activated and available for users at the initial deploy out. And as an admin, like you're going to want to do this before you start adding a bunch of other stuff in to your configuration. So I really recommend just the usual Kubernetes application YAML. So there's that. And then we got just more deep links for all the various stuff. And then these are the two engineers, Deep and Anusha, who work at Docker, who helped me get some of the details straight on these slides. So really want to give them a bit of a shout out. And that's pretty much it. I think I ran through this really quick, so we have a lot of time for questions. Yes, sir.
You have a storage system that allows you to carve out volumes.
Yes.
Within storage. How do you link all of that?
Very cool. So the question is, if you have a storage system that allows you to carve out volumes, how do you link those volumes into Docker? So if you're running Docker Enterprise specifically, there's the two ways. There's CSI for Kubernetes workloads, and then there's the Docker volume driver for Docker Swarm workloads. And fundamentally, what you do is you hit the docs, and then write a driver the driver is basically a gateway between the container orchestrator and your storage system. So, like in the Docker volume driver example, what will happen is you'll create a web server that's the driver, and it exposes a web interface that Docker will talk to. And so you have to have a handful of verbs in your API that to a spec that we've written, and basically it's create a volume, get a list of volumes, mount a volume on the system, unmount a volume on the system, and that's basically the only verbs that Docker supports for the Docker volume driver. And then so what'll happen is your plugin's just sitting there running away, not doing anything until Docker says, hey, we need a volume created on that driver, and here's we want a volume of this size and these capabilities. And typically the way Docker works is it's just pass through command flags or pass through API snippets in JSON when you're making the API request, and then those get sent to the driver on the node that Docker has scheduled the volume on. And if that volume doesn't exist, then it should fall through to a create, and then it'll mount the volume. And then once that volume is mounted on the system, and the file system's created and prepped, then it'll hand that volume. Then you'll basically just hand the mount point via API call back to Docker. The kube CSI drivers are basically the same concept, except that it's a bit more push from kube. And well, it's a little bit different. Kube actually works on like a notification polling system. Kubernetes is just a giant state machine. So what'll happen is that when Kube wants to create a volume, it'll basically create a volume request, and then your plugin will see that request in the queue, and then do all those operations. And then with Kube, it's a little bit different because it's also the concept for Kubernetes is way more operator driven than the Docker concept is. Docker is basically very user driven. If you want to create a volume on Docker and you're a user, you just say, hey, I want a volume, and we expect the system to bring you a volume. For Kubernetes, you create storage classes, so you can actually have multiple storage classes with your one storage provider. So if you want to have a storage class that has like 3 replicas, that has 3 replicas per volume that you create, and then you have a cheap storage class for whatever that you don't even care that it's that you've got replicas on. You can create separate storage classes for that, but it's expected that as the storage operator, you'll go ahead and carve out resources for that pool, and in certain cases, even individual volumes for that pool, or you can also determine that pool to be a dynamic provisioning in Kube. Kube gets a lot deeper. Yep. Any other questions? Yes, sir.
What was the reasoning for the snapshots and the resizing to be separate containers versus, say, the controller?
Question is, what was the reason for the extra feature, snapshots and volume resizes being extra, like running in separate containers? That's the way Kube does stuff. It's a Kubernetes convention that these sidecar containers is what they're called, like add extra features to your application. And what's really funny is under the hood in Kubernetes, for your driver, for your actual driver, there's a Kubernetes provided sidecar that implements the Kubernetes side of the CSI spec. So I don't know if the same approach is used in the not Pivotal or the other systems that support CSI yet. I don't know if they do it that way as far as creating sidecars that you need to run to make your driver work. But it's just kind of a Kube convention. It's the microservices approach. What you totally can do is you can bake all of these APIs into one kind of monolithic container. And then just spin up multiple copies of that monolithic container for each role. And a lot of people do that, but you don't have to. You can actually microservices the whole thing out on all you want. Any other questions? All right, cool. I have some Docker stickers up here, if anybody wants them. I have one vintage Docker Swarm sticker. So whoever gets up here fast enough gets to have it. Thanks, guys. Appreciate it.